Hello, welcome to KiboCUBE Academy, Lecture 12, Introduction to Nanosatellite Mechanisms. My name is Hiraku Sakamoto. I am an associate professor at the Department of Mechanical Engineering, Tokyo Institute of Technology in Japan. I have been studying space deployable structures, especially membrane deployable structures, and also developing small spacecraft. I was a principal investigator for the 3U CubeSat OrigamiSat-1 launched in 2019. I used the development experience of OrigamiSat-1 in Lecture 11, Introduction to Nanosatellite Structures. Today, I will use OrigamiSat-1's example again to share with you lessons learned during the actual development of nanosatellite mechanisms. Today, after the introduction, I will cover 5 important aspects of nanosatellite mechanism design. Then I will explain various common elements of mechanisms, and I will talk about 3 development examples. As an introduction, first, let me show you the same figure that I used in Lecture 11, Introduction to Nanosatellite Structures, because many things are in common between mechanism design and structure design. So I recommend listening to the structure lecture first before studying this mechanism lecture. Mechanisms are onboard devices whose function is based around mechanical movement. To develop mechanisms, first of all, you need to be familiar with structural engineering theories. But for nanosatellites, the resources, meaning mass and volume, are very limited. Therefore, your mechanism affects the other subsystems on the entire satellite, and vice versa. These couplings are very strong, especially in nanosatellites. So it is important to be familiar with the entire system of the satellite when you develop mechanisms and structures on nanosatellites. Today, you will learn how mechanisms are developed and used in the nanosatellite life cycle. Then after I explain common elements of mechanisms, I will share lessons learned during the development of these 3 kinds of mechanisms in actual projects. First is the deployment detection switch on 3U CubeSat OrigamiSat-1. 3 pins are complexed inside the satellite deployer on rocket. When the satellite is released, these pins pop up by spring force. When all the 3 pins are successfully pulled, the power of the satellite is turned on. This is a very common mechanism and very important for your successful mission. The second example is a deployable solar panel on board Hodoyoshi 3 and Hodoyoshi 4 satellites. In order to generate larger power in space, these satellites deploy solar panels to increase the area of solar cells facing the sun in space. The third example is a deployable membrane on OrigamiSat-1. This is a ground deployment test. A 1 meter by 1 meter membrane is deployed out of 10 centimeter by 10 centimeter by 10 centimeter storage volume. On the membrane, thin film devices can be attached throughout the membrane. This technology will be used to realize solar array or array antennas made of a membrane in near future. Anyway, I will explain the mechanism development procedure taking these mechanisms as examples. Again, let me show you the same figure that I showed you in Lecture 11 on nanosatellite structure. This shows a typical mission life cycle of nanosatellites from start of development to the end of operation. We usually develop the breadboard model, BBM, for both electrical and mechanical systems. This is an iterative process. An engineering model, EM, is developed for qualification of the design. Next, flight model, FM, is developed and tested for acceptance to a rocket. Then it is launched, the satellite is deployed from a rocket, and it is operated until the end of life of the satellite. Let's observe this life cycle more closely, focusing on laws applied to the satellite with mechanisms during this life cycle. In the production phase, handling load is applied on the ground and the mechanism should pass the functional test in gravity. It should pass vibration and shock tests where large forces are applied. In thermal tests, the mechanism will experience loads due to the thermal deformation of materials. Your mechanisms should be strong enough to withstand loads during transportation. During the actual rocket launch, the satellite is subjected to strong launch loads. Once in space, the satellite is released from a rocket. There is a deployment shock, the thermal conditions drastically change, and the satellite receives the effect of radiation. Now, if satellite has a deployable structure, when the structure is deployed, there are shock loads caused by hold and release mechanism, HRM. Inertial forces are applied due to deployment dynamics, and there will be a deployment completion shock load. Also, the attitude of satellite will be disturbed due to the deployment dynamics. This may cause additional inertial forces or torques. Finally, after the deployment of structure, a satellite typically becomes more flexible. So during operation, the satellite may vibrate. You have to consider the flexible structure's vibration during operation. In lecture 11, I explained the natural frequencies of structural system. So let me discuss the required natural frequencies of the deployable structures in satellite life cycle. This discussion will clarify the characteristics of the mechanisms. During the launch of the rocket and release from a rocket, the satellite needs to be quite stiff and strong. For example, for CubeSat on ISS Kibo, the lowest natural frequency of the system is required to be larger than 60 Hz. Thus, all the mechanisms should hold the structures stiff enough. Then once the holding mechanism is released, then for example, the structure starts to deploy. It is almost a rigid body movement. Thus, the natural frequency of the structure during the deploying motion is almost 0 Hz. So the release causes the drastic change of the natural frequency from about 60 Hz to 0 Hz. Usually, holding and releasing are realized by one mechanism. So this is often called a hold and release mechanism, abbreviated HRM or HDRM. During the deployment motion of the deployable structure, sometimes other mechanisms are used, such as a deployment control mechanism, motion synchronization mechanism, or damping mechanism to dissipate deployment completion shock. After the completion of the structure's deployment, the satellite needs to be stiff enough to suppress the flexible structure vibrations. To stiffen the structure, we often use a latch mechanism. So during deployment, the natural frequency was as low as 0 Hz. Then the system was latched to have a natural frequency somewhere around 10 Hz, for example. The natural frequency should be high enough to enable precise pointing towards the target location, such as on the Earth or in the sky, for some applications. If the satellite is still flexible, precise pointing will not be feasible. So please be aware of the change of natural frequencies realized by various mechanisms on satellites. Now, I will show you a typical design process for nanosatellite mechanisms. The first step is to identify all the requirements and constraints. Then the basic configuration of the mechanism is conceived. An effective method is prototyping and testing. You will repeat this process several times until you determine the configuration. In this process, it is important to design proper verification methods for your mechanism at the same time. Some tests require large facilities, such as large space and high ceiling with gravity compensation mechanisms. Some numerical analysis is very difficult to conduct, such as a geometrically nonlinear finite element method or a transient nonlinear dynamic analysis. You may need the participation of a specialist in numerical analysis. Thus, you have to consider your constraints from the development environment or resources you have. If the mechanism design does not facilitate verification, you will avoid the design. After the basic configuration is determined by prototyping, you will carry out numerical analysis using a finite element method. FEM was described in lecture 11. Then you will proceed to the fabrication of an engineering model and quantification tests. Finally, the flight model is then constructed and tested. During the prototyping and testing, it is important to clarify what the deployment assistant forces or torques are and what the deployment resistance forces or torques in your mechanisms are. So first, please list what the factors of these forces or torques are. This figure shows an example of the torques in the mechanism of reflector deployment. A positive value is a deployment assistant torque, and the negative values are deployment resisting forces. Second, please estimate each magnitude. These estimates are used for planning and evaluation of analysis and tests for the mechanism. In addition, please watch out for the effects of temperature. Friction may increase due to thermal deformation and misalignment. Finally, also watch out the nonlinearity of assistance or resistance forces. They may vary from the beginning to the end of deployment. So please watch the change in forces and torques, mainly by testing on the ground. Now I'm going to talk about the 5 important topics in nanosatellite mechanisms. First, let's review the typical launch laws applied from a rocket to a satellite. They are often categorized into 4 types with different frequency domains. For KiboCUBE's launch vehicles, random vibration conditions and quasi-static acceleration conditions are specified. The satellite, including mechanisms, are required to be stiff enough and strong enough to withstand these loading conditions during the launch. Another important topic is tribology. Tribology is the science and engineering of interacting surfaces in relative motion, including lubrication, friction, wear, gouling, and bearing design. The high vacuum environment in space has significant effects on sliding parts of the mechanism. First, there is evaporation of lubricants. At low pressure, even solid-state lubricants evaporate. Evaporation should be considered, especially for liquid lubricants, such as oil and grease. Thus, the selection of appropriate lubrication methods is important. Usually, solid lubricants are used on satellites. The second is cold welding. Metal surfaces stick together due to an increase in the friction coefficient. This is called cold welding. This is caused by a delay in the formation of the molecular absorption layer and oxidized layer on the material surface. Typically, these are protective layers with low friction. After the protective layer is worn off on the metal contact surface due to the launch vibration or other loads, in the air, oxidation occurs quickly and the protective layer is repaired. In contrast, in a vacuum, the repair is slow and the worn surfaces touch each other, resulting in high friction. Thus, we need countermeasures. There are 4 possible countermeasures for cold welding. First, metal and metal contact causes cold welding. Thus, one of the 2 contacting surfaces may be made of a polymer material. For this purpose, a polymer material with high rigidity and strength, such as PEEK resin, is often used. Second, even when metal and metal contact, if a different alloy is used for contacting surfaces, we have less cold welding effect. Third, a hard anodizing treatment is applied to aluminum surface to produce a hard surface layer for avoidance of cold welding occurring on the aluminum alloy surface. This treatment is required for CubeSat rails. Finally, solid lubrication is used. Often, we use MOS2 on contact surfaces. It is one of the most widely used lubrication methods in space. It has good thermal stability. However, be careful of the wear caused by vibration load called fretting wear. In addition, please note that the lubrication property degrades due to moisture absorption in the air. Other than the high vacuum, the space environment strongly affects the satellite's mechanisms. Here I explain three most significant effects. First, atomic oxygen, AO, exists in low Earth orbits. Many polymer materials are strongly oxidized by AO, resulting in gradual loss of the material's surface. This is called erosion. Polyimide and carbon fiber reinforced plastic, which are often used as space materials, are also subjected to erosion by AO. Special attention should be paid to deployment mechanisms such as solar panels. They are exposed in space outside of satellite structures, so please be careful for its lifetime. The same is true for ultraviolet waves or other space radiation, which are much stronger in space than on the ground. Typically, UV radiation causes photooxidative degradation, which results in the breaking of polymer chains and reduces the molecular weight, causing deterioration of material properties. And third, the thermal environment can be quite harsh in space. Please note that thermal deformation can cause fatigue. In addition, it can change the alignment of the mechanism, and it may cause the higher friction during the motion of the mechanism. As the next important topic, I will talk about verification methods for nanosatellite mechanisms on the ground before the launch. Verification usually consists of test, analysis, inspection, and demonstration. And when you carry out tests on the ground, you sometimes need gravity compensation or gravity offloading system. The deployment behavior of mechanism, typically a deployable structure, is greatly affected by gravity and atmosphere. To reduce the gravity effect, offloading methods are required to better produce deployment assistant force and deployment resistance force. Basically, gravity affects deployable structures in three ways. First, please watch out the gravity effect on the gap in your mechanisms. Movable mechanisms usually have some gap, but on the ground, parts are pushed vertically downward due to gravity. This pushing is not present in microgravity. So deployment assistance and resistance forces change. Second, please consider geometrical stiffness. The deployment structure is often flexible. It is stiffer on the ground than in microgravity due to stiffening caused by its weight. I will talk about geometric stiffness later. And finally, the effects of deflection of the structure due to gravity can be significant. Typically, for this reason, during and after deployment, gravity compensation or gravity cancellation, gravity offloading is often used to avoid large deformation due to its own weight. Methods include hanging from a high ceiling with threads, floating using air-bearing, air-filled hockey table, floating on water, or sinking in water, or you may use wheels and other methods. Together with gravity offloading, please consider the effect of air drag. In the case of dynamic deployment, the deployment speed is reduced on the ground due to atmospheric drag. So the important message here is the following. For you to design a good mechanism, you need to design a simple ground experiment method simultaneously. Second, I will talk about numerical analysis as a verification method, especially for deployable structures. So linear modeling in the finite element method is often used. Model vibration analysis and stress analysis are carried out to evaluate the stiffness and strength of the structures. Please see lecture 11, structure lecture. Another type of numerical analysis is dynamic transient analysis. So this is an example. This is a dynamic transient analysis of the small solar power cell demonstrator, Icarus. This analysis was to verify the attitude stability of the cell craft during membrane deployment. In this kind of analysis, the equation of motion is calculated with advancing time by delta t from an initial condition. In each time step, the equilibrium of stress and displacement is calculated. Equation of motion is a differential equation. Thus, this is an integration process. This kind of transient response analysis is used when nonlinearity is high and when it is difficult to evaluate only with linear vibration mode analysis. Another method in numerical analysis is called the geometrically nonlinear finite element method. The common finite element method, FEM analysis, is linear analysis. The linear analysis model assumes that the stiffness of the structure, such as bending stiffness, does not change between an undeformed state and a deformed state. This is well applicable for small deformations of stiff structures. However, when we consider out-of-plane deformation of thin plates, for example, the out-of-plane stiffness changes due to in-plane tension and compression forces. In other words, a structure with stiffness K sub 0 in the undeformed state changes its stiffness to K sub 0 plus K sub G in the deformed state due to the change of stress distribution. The second term is called geometric stiffness. To consider the geometric stiffness in FEM, the load is gradually increased and the stiffness value is updated in every step. Stiffness at each step is called tangent stiffness. Equilibrium displacement is calculated by using this tangent stiffness matrix in every step. This is called geometrically nonlinear FEM and can be implemented with commercially available FEM software. So if geometric stiffness is not negligible in your system, you will consider using it. The final topic related to the nanosatellite mechanism is an advanced topic. It is about control structure interaction. When you deploy a relatively large and flexible structure after the deployable structure is deployed in orbit, the natural frequency is usually low. In this case, due to attitude control actuators, such as reaction wheels, a flexible deployed structure may vibrate. If the flexible structure vibrates in a satellite that requires accurate attitude control, attitude stability will be poor. Therefore, generally, attitude control actuators are driven by input signals that contain sufficiently lower frequency components than the lowest natural frequency of the flexible structure. And vibration amplitude and attitude stability can be estimated and evaluated by the following method. First, vibration modes of the flexible structures with fixed satellite attitude are predicted by FEM or experiments for a few lowest vibration modes. This is called a constraint mode. Then second, an unconstrained mode is constructed by combining a constraint mode into the dynamic equation of the satellite system, and the attitude control is simulated. Now I talk about elements of mechanisms commonly used in nanosatellite systems. The first element is non-metal rock wire. This is very commonly used for various hold and release mechanisms on nanosatellites. I have 5 slides to explain this mechanism element. I take OrigamiSat-1's deployment antenna as an example. So we wrapped the 2 sulfur bronze convex tape antennas around the satellite structure. The shorter antenna is wrapped first, and then the longer antenna is wrapped on the top of it. Then we restrained the tip of the longer antenna with Vectran threads fixed to the satellite body. These threads are burned with nichrome wires. I am going to explain this part more closely. So we tied 2 strands of threads to the hole at the tip of the antenna using bowline knot. There are 2 strands because of redundancy, and we put polyimide tape to the antenna tip hole to protect the threads. Then we tied one of the threads to a hole around the bobbin using a bowline knot. Then we wrapped the thread around the bobbin and reeled in it. The objective is to control the tension. We adjusted the length of the thread by using mark on the thread. In addition, we used the mark on the antenna to make sure that the looseness of the antenna is within the prescribed value that will not interfere with satellite release from the rocket. There's a method preventing the bobbins from rotating. We fastened the screw of the bobbin using a torque driver, and also we tightened 2 bobbins with thin stainless steel wire. These figures show our bobbins. We passed 2 threads through the thread wrapping part. The flange constrains the threads to move in out of plane direction. We made sure both threads touched to nichrome wires. The measurements of range of tension and of tensile strength, as well as stretching out until saturation of elongation were conducted. First, we measured the allowed range of tension. We found the minimum tension is 0.42 Newton, and the maximum tension is 2.12 Newton. So we also measured the tensile strength of the thread, and also we measured the strength of the knot. Finally, these photos show the preparation of the threads. We stretched out the threads by applying loads for a long time until the saturation of elongation. The threads was pulled by weight, and this is a laser displacement sensor to monitor the elongation. Here I show a typical checklist for a non-metal lock wire system. First, please evaluate the safety factor, meaning the strength of the threads in tension. In the case of excessive tension being applied, there are several methods. One option is to use a lever mechanism to generate a large holding force with a smaller thread tension. Another is simply increasing the number of threads. But when increasing the number of threads, please make sure that the tension is applied evenly to each thread. Please evaluate threads change in length due to creep deformation. And please choose proper knotting method. Please make a procedure manual to ensure repeatability of knotting. And stretch out threads and knot until saturation. After making knots, please apply force to stretch threads before use. Please evaluate the strength of the knot. Please evaluate the strength of knotted threads, as threads will be complexed at the knots and the strength is significantly reduced there. Please consider the double redundancy of the mechanism. And please remove any sharp edges to avoid the threads rubbing on the sharp edges and losing strength. And finally, please determine the inspection procedure for the flight model and practice the procedure well during the development process. Now, let's talk about the springs and convex tapes. These are commonly used as actuators combined with a hold and release mechanism. Again, the force and torque estimation is important. And here's a tip. When the structure is deployed, elastic energy stored in the spring is converted into kinetic energy. Thus, inertial force usually assists deployment. But in most satellites, the required force or torque is determined so that the structure can be statically deployed from any position of the deployment motion. For spring and convex tape deployment, please watch out for the shock load at the end of deployment. When the deployment is completed, the shock force is applied by a collision with a stopper, for example. This is difficult to estimate, especially for a large deployable structure because of the air drag. The deployment speed may be slower in atmosphere. Thus, deployment compression shock may be greater than in vacuum. This movie shows an example of a deployment test of a deployable membrane in vacuum chamber. The deployment conspiration was not very successful in this model. Convex tapes are used as elastic hinges. Conventional hinges on motors have a risk of being stuck because they usually involve a sliding motion. Therefore, elastic deformation of convex tape is often used to eliminate the risk of stuck. A commercially available Carpenter's tape measure is often used in nanosatellites. However, since free deployment causes large shock force when deployment is completed, the deployment speed may be controlled by motor as a deployment velocity control mechanism. This kind of mechanism is often called STEM, storable tubular extendable member. So this movie shows the STEM made of carbon fiber reinforced plastic on board the 3U CubeSat OrigamiSat-1. So let me introduce pyrotechniques and non-pyrotechniques as commonly used hold and release mechanisms. Conventionally, pyrotechniques such as pulling out rings, cutting wires by explosive pressure were commonly used for satellite and rocket separation because of their high reliability. They are called separation nuts, separation bolts, wire cutters. Pyrotechniques are highly reliable, but usually generate a high shock force. They are also costly because they are often not reversible. Therefore, in recent years, non-pyrotechnics HRM are often used. They are called flange bolts, pimplers, and ejectors, typically using shape memory alloy actuators. Some use paraffin actuators as well. However, since they are usually used with preloads, a relatively large shock load is still generated. So motors may be your choice, and motors are often combined with bearings. If the inertia of a deployed structure is large, or if the deployment shock is a problem, a motor can be used for low-speed deployment, and it has excellent velocity control. And since the motor is reversible, there is a possibility of realizing storing after deploying. Generally, step motors are used because they are easy to control, but their torque is low. Thus, they're usually used with the reduction gear. The problem is that the motor usually have temperature limitations. This is because the characteristics of internal clearance and bearing change due to temperature change. Therefore, temperature control with temperature sensors and heaters is often required. This may add some complexity to your system. Regarding bearing, with oil, grease, or solid lubricated ball bearings, plain bearing are available for space applications. The final mechanism element is inflatable. Inflatable structure deployed by filling a balloon-like membrane with gas. Various missions have demonstrated this kind of mechanism in orbit. As method of gas generation, some use compressed gas and some others use sublimating compounds. These figures show the inflatable structure demonstration satellite Sprout developed by Nihon University in Japan. From now on, let me show you 3 development examples. The first development example is the deployment detection switches on the CubeSat OrigamiSat-1. There are 3 switches to turn on power of the satellite when the satellite is released from the rocket. The switches are at the bottom of the rails, and this is the stored configuration in the rocket. Before release, the pin is pressed by the CubeSat deployer on the rocket. After release, this pin moves outwards using a compression spring. This pin movement turns on the micro switch. After the flight model vibration test, our deployment detection switches 1 and 3 did not work due to the adhesion of pins. After investigation, 3 reasons were identified. First, the manufacturing dimension was not appropriate. The holes for flight model pins were slightly smaller than the engineering model's holes. Second, the surface roughness of the pins were not appropriate. The flight model pins had scratches on the surface due to improper handling, resulting in high friction. Third, the microswitch was misaligned. We found that the friction between the pin and hole was larger in the flight model than in the engineering model because of poor alignment adjustment during the flight model assembly. Then after the following 3 improvements, the second flight model vibration test was conducted, and we could verify the proper functions of all deployment detection switches. Regarding first error, the hole diameter was enlarged within dimensional tolerance. Second, after scratches on the pin surface were removed, MOS2 coating was applied. And finally, alignment was carefully adjusted during the reassembly of the flight model. These pins worked well in the actual flight. Next example covers the development of deployable solar panels on small satellites. The small satellites in this example are Hodoyoshi 3 and Hodoyoshi 4. I am showing these examples through the courtesy of Mr. Yuta Araki, who was in charge of the development of these mechanisms. Hodoyoshi 3 and Hodoyoshi 4 were launched together by Donyepur launch vehicle in 2014. The solar panels were successfully deployed on the first pass over Japan. So I'm going to talk about 2 kinds of mechanisms in this deployable solar panel. First is the hinge with the latch, and the second is the hold and release mechanism. This is the solar panel, and there is 2 hinges with the latch. The hold and release mechanism is here, and there's a bracket on the solar panel. This is a side view. There are 2 solar panels, and the HRM holds the bracket on the solar panel. By sliding the bar in the HRM, the solar panels are deployed by torsional spring in the hinges. And the hinge is latched at the right angle here. First, I will explain the hinge with the latch. In the developed mechanism, the latch is applied by inserting a latch pin into a hole drilled at an arbitrary angle. In this case, it is 90 degrees. The hinge and latch mechanisms are integrated into one unit to significantly reduce the size and weight. If necessary, the dimensions can be changed according to the panel size and required torque. This feature enables to accommodate a variety of solar panels. Then this is a hold and release mechanism developed in Hodoyoshi 3 and 4 projects. A so-called gate bar method is used with a thread burning mechanism. Similar to the OrigamiSat 1, there is a tension adjustment mechanism for the non-metal lock wire. And also there is a micro switch for checking the proper motion of the gate bar latch pin. This is a simple, compact, lightweight, and low-cost mechanism. Simple means there are only a small number of parts. So these 2 lines are threads. They are redundant. There are tension adjustment screws, and there are heat cut devices. When the threads are burned, this gate bar pin slides to the right, and the bracket here is released. But there were problems during the development. The mechanism did not work properly during development on the ground. So after verifying the function of the hinge with the latch and HRM, a deployment test was conducted with mechanisms installed in the satellite. By the way, no gravity compensation system was used in these experiments because the solar panels were small enough. So neither the solar panels opened. On one side, the HRM worked and the solar panel started opening but stopped in the middle of the deployment. It was found that the hinge was very stiff after assembly. On the other panel, the HRM did not work, and the solar panel did not start deployment. Threads were properly bound in the HRM, but the gate bar pin of the HRM was engaged with a bracket on the solar panel. Let's observe this error more closely. So the panel deployment stopped in the middle. After investigation, they found that this was caused by the misalignment of the rotational axis of two hinges. This misalignment occurred when a solar panel with hinges was assembled to the satellite body. To avoid this problem, of course, it is carefully reassembled. In addition, two design improvements were made. First, the clearance between the shaft and hole of the hinge was changed from 0.1 mm to 0.4 mm in order to absorb distortion during assembly. Second, a stronger torsion spring was used. The deployment torque of the hinge was increased by about 5 times. What about the other error? The HRM gate bar pin was not pulled out completely in the other solar panel. So it was suspected that friction between the HRM gate bar pin and the hole of the solar panel bracket was larger than expected. Before threads are burned, the spring force to pull the gate bar pin also applies perpendicular to the pin because of the gap clearance of the hole. This results in an increased friction. This effect had not been properly taken into account, so the resistance force was underestimated. The resistance force due to friction was estimated again. Furthermore, to reduce the friction, two design improvements were implemented. First, Teflon bush was added inside the hole as a solid lubricant. Second, the edges of the hole at this contact point were rounded with a larger radius of curvature. After these design improvements, the panels were carefully reassembled. The perpendicularity and positional relationships of each parts were adjusted carefully using SIMS during assembly to achieve better alignment. Then deployment tests were conducted successfully at 0 degrees and 40 degrees Celsius in a thermostatic chamber. This development leads to the successful flight operation of Hodoyoshi 3 and 4. As the last example, I will talk about the development of a deployable membrane structure. So OrigamiSat 1 has a 1 meter by 1 meter deployable membrane stored in a 1 unit size, and 4 walls open when cutting the 2 strands of threads by nichrome wires. The threads cutting mechanism is similar to the one in the deployable convex antenna, but the size is smaller. For improving burning reliability, 2 systems of nichrome wires, A and B, are used in parallel. So there are 2 nylon threads and 2 nichrome wires. First, the thread is looped using a double sheet bent knot. This loop is tied to the end of a holding arm with a loop knot, then passed through the nichrome wires to each bobbin, which is then wound and screwed. This movie shows the ground deployment test. The satellite is in this configuration first, then the membrane is deployed. This test was achieved by using gravity compensation. There are 4 threads to hang the tips of 4 diagonal booms from the ceiling. Since it is difficult to completely simulate on-orbit dynamics on the ground, the effects of each deployment assistance forces and the deployment resistance forces are separately estimated by various experiments and analyses, like in this chart. However, a system-level test is still needed. If the estimated forces are not validated before launch, there is always a risk. To reduce risk, we should make efforts to simulate on-orbit conditions as much as possible. And one method is test with gravity compensation, like this. But this method usually requires many trials and errors. For example, what is the appropriate length of the gravity compensating suspension threads for this deployment test? These are very difficult but interesting problems. I believe these trials will lead us to the development of innovative space systems in the near future. Here I conclude my lecture today. These items summarize my talk. It is extremely difficult to predict all failure modes of mechanisms without actually manufacturing and testing. The mechanism is normally more difficult to analyze than the usual satellite structure, so early prototype is essential. So please repeat manufacturing and testing from the mock-up level to identify all failure modes as early as possible. Watch out for an increase of resisting force torque due to misalignment caused by dimension tolerance, cold welding, assembly error, and thermal deformation. And finally, please design proper experimental methods on the ground to enable verification of the mechanism's function. You now know that these are iterative processes, so early validation and verification are always the keys to the successful development of nanosatellite mechanisms. Thank you very much.